I'm Tim Ventura, and we're joined today by Dr. Harold Sonny White, a mechanical engineer, aerospace engineer, and applied physicist known worldwide for his groundbreaking work in emerging energy and breakthrough propulsion physics. Dr. White has a bachelor's in mechanical engineering from the University of South Alabama, a master's in mechanical engineering from Wichita State University, and a PhD in physics from Rice University. His career experience includes roles at industry-leading aerospace organizations such as Boeing, Lockheed Martin, and NASA, where he was awarded both the NASA Exceptional Achievement Medal and the Silver Snoopy Award. Since retiring from NASA, Dr. White has worked as Director of Advanced R&D at Limitless Space Institute, along with his newest role as founder and CEO of Casimir. So, Sonny, welcome. It is truly an honor to have you with me today, sir.
It's great to get a chance to do this with you, right? Thanks for all the stuff that you do in terms of trying to, capture and record and explore all the things associated with bold visions for space exploration, right? So we tend to be a very passionate lot about what we would love to see happen at some point in the future, right?
Absolutely, absolutely. Well, and thank you in return for decades of leadership in emerging propulsion and basically pushing the envelope in terms of technology, science, and physics in this area. You have been out in front for so long. It is, again, truly an honor to be able to interview you.
Thanks for the comments. That's really, really kind of you, sir. I think thinking back through history, my journey started very early in this domain. I don't want to intimate that it was like a straight linear path that I knew from 16 that I was going to do this. But looking back, when you look back on your journey, you can certainly see some of the things that had currency with your soul and kind of helped shape you and motivate you. As I do remember as a teenager growing up in Washington, D.C. area, I got quite a number of opportunities to go to the National Air and Space Smithsonian. This is back in the 80s. I'm dating myself by saying that. So I used to go to the National Air and Space Smithsonian in the 80s, and it always landed on me very strongly, kind of walking in and around those great halls with all of these illustrations of amazing engineering achievements that people had accomplished, pushing boundaries and overcoming obstacles and going higher and going faster. And, Tim, it's not just the things that resonated with me. It was the stories, right? They would always have stories, right, about the people that were involved in all of that. And I think the combination of the two really kind of landed on me. And I was always a little bit of a technical wonk. I would take things apart and oftentimes not be able to put them back together, much to my parents' chagrin. So I think looking back, I can see now I was destined to become a scientist and an engineer. And so, that's just, I think the seeds were planted very early. But like anything in life, sometimes you have a lot of different circuitous routes that you take to get there. I started working in the space program at roughly around 2000. Although my passion is advanced power and propulsion, as you know, right, the first half of my career was connected with flight robotics, right? So I actually got a chance to support the space shuttle. I was a subsystem manager for the robotic arm on the shuttle, and eventually became the subsystem manager for the station robotic arm. I sat on console for every mission that built the International Space Station. So certainly have a good appreciation for the idea of teamwork, how teamwork scales at the ultimate level, right? The International Space Station is a wonderful illustration of that. But my passion is and always has been advanced power and propulsion. And so I was a very faithful servant in the robotics role, but I was always looking for opportunities to communicate ideas, right? And so my stakeholders and management recognized my strong interests in this area and eventually looked for an opportunity to kind of move me into that role where I could play a little bit of a leadership role at the agency level in that domain. And Tim, one thing I take some comfort in working at the agency. I remember when I started, the parlance used to always be Mars is the ultimate destination for human space exploration, right? And if you say that, right, if you say Mars is the ultimate destination for human space exploration, technically we can do that with chemical propulsion. We just got to, we got to live with 180 to 220 days to get there and get back. And so that kind of sets up a situation where it closes a discussion, right? And so I worked really hard. Bill Gerstenmaier was at the head of HEOMD at the time, and I was working on some things at the headquarter level, and I worked to try and change the parlance, right? And so what you kind of see now is the parlance is Moon, Mars, and beyond. And so that operative word beyond is a really important departure from that first statement, right? Because it sets up an opportunity where you can ask the salient question, all right, if the ultimate destination with human beings is beyond the orbit of Mars, right? What does that require? And so that's a great opportunity that then forces us to go ask questions and find out really quickly, yeah, chemical propulsion is just not going to do that, man. So anyway.
Yeah. Well, and you have been in this leadership role. I mean, conference after conference after conference, right? I used to see you when you were attending the STAFE conferences. You have been developing.
That takes us back. Yeah, that's awesome.
Yeah, so it goes back a long ways. You have been in this area. You developed basically a new way of reworking the Alcubierre drive, right, with the toroidal field to reduce the power requirements. And I'll come back to that later. So there has been a ton of work. And then what you're working on now, kind of my feeling there is it is shrouded in technical language that a lot of people don't understand. And so they may miss it. And when I read through it at first, I was like, wow, that's interesting. And then I was like, oh my God, he is harnessing 0-point energy, right. And so again, this is, I mean, you talked about stories and culture. These are stories that would not have been believable 50 years ago, right?
Right.
The fact that you are, I mean, again, but so let me get into that though. Your company Casimir is developing energy technology to harness the Casimir effect, which is based essentially on wavelength exclusion between closely spaced plates. Now, in normal circumstances, this creates a force that would push the plates together once, but you've developed a nanotech device that generates continuous power, right?
Right. Yeah. So that great way to set things up for me. So let me kind of play some stuff back to you. Casimir is working to mature and commercialize some power generating nanotechnology, some nanostructures that we've engineered, kind of a customization of the Casimir cavity concept. And that structure interacts with the quantum field or the quantum vacuum in such a way that it causes preferential flow of electrons from one location of material to another location of material. So let me kind of back up just a minute and give a little bit of a preamble on the Casimir force phenomena, right? Oftentimes when I'm talking to folks about what we're working on, and I say we have this nanotechnology that harvests energy from the quantum field or the quantum vacuum. I usually start by spending just a second addressing the word vacuum, right? Because when we hear the word vacuum, right, we have a mental model, maybe pictures a steel vacuum chamber. It's got vacuum pumps on it, and you push a button and pulls all the air out, and that's a vacuum, right? And we associate the word vacuum in that context with nothing, right? But what quantum mechanics tells us is that at the microscopic level, empty space isn't empty. It's full of fluctuating fields and forces, virtual particles, virtual ephemeral fermion, anti-fermion pairs, and photons. It's just a sea of activity. And so this sounds very contradictory to what we think of when we think of the word vacuum, right? Now, as peculiar as all this might sound to folks listening to this, there is a real classical observational consequence of this peculiar nature that I'm kind of articulating right now, and that is known as the Casimir forces, as you were saying, Tim. And so you can think of it in the following way, and I'm going to use some hand puppets, and we'll see how well that communicates to folks. If you imagine you took two metal plates, like my hands are two metal plates, and you put them very close to one another, the separation distance here is maybe 100 nanometers. So a red blood cell would not fit between the gap.
Yeah.
Then we put these two plates in a real vacuum chamber, and then we close the door, push the button, and pulls all the air out so that it is a classical vacuum. There's nothing in there. It's a perfect vacuum. And then we could imagine if we could go down to a microscopic level and measure the pressure on the outside of the plates and the pressure between the two plates. So we're going to pretend for a moment that, Tim, you have superpowers. You were bitten by a radioactive spider, and you can shrink yourself down to a wee tiny atomic level. We're going to have you go measure the pressure on the outside and the pressure on the inside. And you're going to expect that you're going to measure 0, 0, 0 based on our everyday definition of the word vacuum. Yeah. What you're going to measure is you're going to measure 0, 0 on the outside, as you expect, but you're going to measure a negative pressure between the two plates. Well, what the heck is going on? How's that even possible? Well, you heard me say that empty space isn't empty. It's full of fluctuating fields and forces, these little bits of energy, if you will. And you may remember from university, the parlance, matter is both a particle and a wave, right? So all these little bits of energy have wavelengths associated with them. So when we add up all the bits of energy on the outside, it's unrestricted, and we get a number, and that's technically our zero reference, right? But when we add up all the bits of energy that appear in between the two plates, any bit of energy with a wavelength wider than that gap, it doesn't contribute to the integral or the addition of all these bits of energy. So there's a deficiency of vacuum energy between the two plates that's coupled to that negative pressure, right? So there is a lack of vacuum energy between the two plates that results in a effective negative pressure between the two plates, and that results in a force that wants to cause these two plates to collapse, and that's called the Casimir force. Now, this idea was derived by Casimir in 1948. He was working with fluorescent light bulbs and cathode ray tubes, which it's like, what the heck does that have to do with that? He's the guy that derived it, and that's what he was working on at the time. But the physics community didn't measure the Casimir force to everybody's satisfaction until 1996, 1997. Lamoureux and company were the first to measure it. And it's been measured hundreds of times since in many and varied ways. There's also a transverse Casimir force. So if you try to slide the two plates relative to one another, the quantum field impedes that sliding motion. So the quantum vacuum, or this peculiar nature of reality at the microscopic level, is a very real thing, and it has real observational consequences. Now, independent of our innovation, the following is true from a logic precedence perspective. Those two plates in the quantum field set up an asymmetry that results in a force that wants to close the gap. And so when you have those two plates in the quantum field and you allow the quantum field to act on them, it will apply a force over a distance, and that's the definition of work, or energy, if you will, a Newton meter. And so the quantum field acting on these two plates will provide a tiny pulse of energy. Now, the problem with the textbook definition of the Casimir cavity, like we're talking about, is that once the plates have collapsed, you can't get any more energy out of this system. The watch spring has been unwound. You've got to pull them apart. You have to wind the watch spring again. And so this arrangement would only at best be a battery, right? And it would never be greater than 100% efficient. So you'd always have to charge it with something external, if you will. And so I think even if you look in the literature, you'll find some people have written papers over the years kind of exploring that as some kind of a battery alternative. So is there some way we could potentially modify the Casimir cavity concept that might then allow us to continuously extract energy? right? And so that comes to our innovation. And so what we've done is the original Casimir cavity concept, right? The two plates, right? We fabricate chips in a standard nano fabrication environment. We fabricate chips that have the cavity walls, right? But the cavity walls are affixed to the silicon substrate. We do not want them to move. So they are affixed to the silicon substrate. They are electrically connected on the silicon substrate, right? And then in the middle of the Casimir cavity gap, we put antennas. We have pillars that stick up through the gap. They don't touch the walls. They're in the middle, and they too are also affixed to the silicon substrate. So it's like skyscrapers with big poles down the middle of the street, if you will.
Well, and you actually have some of those chips on a plate that you showed me earlier. So
we've gotten really good at making them over the last 5 years. We make all kinds of little prototypes with many cavities on these chips. Getting close to 1 million or more if we can get that, right? So this particular structure, you got the walls of the cavity with the pillars along the midplane, and everything's static, nothing moves. So how does the quantum field interact with this custom structure that I'm describing to you, right? What's the difference, right? And so for that, let me give you a metaphor. Imagine a Pacific atoll island out in the middle of the Pacific Ocean. It's got a wonderful lagoon in the center. And so the atoll island has all this random wave energy in the Pacific Ocean that's battering the outside of the atoll. And you've got this nice lagoon that's in the center. It's very quiescent. And so we're going to imagine that Tim's on vacation and Tim's on a little paddle board on the lagoon and just having a nice quiescent day, enjoying the scenery. You've got a little Mai Tai because there's no wave energy on the lagoon. Even though the lagoon is connected to the Pacific, much of that wave energy cannot manifest on the lagoon. It's a protected environment, right? Yeah. So with this metaphor in mind, let's go back to our Casimir cavity, custom cavity with the pillars in the center, right? And so in the Casimir cavity, this custom Casimir cavity concept, the quantum field is like the Pacific Ocean. It's got all this random wave energy that's battering the atoms that make up the walls. All the virtual photons are causing them to wiggle, right? Now, but the plates can't move. We've affixed those so that they can't move. We don't want them to move, but they can still put energy into the atoms that make up the walls. And so on occasion, a real electron that's in around one of these atoms that make up the wall, a real electron will be stimulated by the quantum field to quantum tunnel to the pillars that are at the center of the Casimir cavity gap. Now, the pillars are like you on your paddleboard. It's a very quiescent environment. There's very little stimulation from the quantum field. So when you calculate the probability of the return current to basically mirror what came in. So, 10 electrons going in, do 10 electrons go back? No, the probability of quantum tunneling back because of the protected environment of the pillars in the center of the gap, the probability of tunneling goes way down many orders of magnitude. And so in this way, this custom structure causes preferential flow of electrons from the walls to the pillars. And so in the limit, right, if you connect this system to a resistor or an LED, whatever, the electrons will go from the pillars back to the walls because they want to go back to where they started from. And then the quantum field will continue to cause the stimulation of the electrons. So in some ways, if you think about like a solar panel has an N-doped slab and a P-doped slab with a depletion region between the two. So there's this N and P stack with a depletion region between the two. Real photons from the sun hit the N-doped region, right? And on occasion, they cause an electron to go into the depletion zone. And then when you connect the solar panel across a resistive device, LED, whatever, the electrons will go back, right? And so the sun will continue this process. And so a solar panel works on the real photon field from the sun. Our devices work on the virtual photon field from the quantum vacuum. Right? And so there's just drawing some parallels there for the purpose of communication. So
No, that's wonderful. And let me put a pin in this one for the audience, because one of the things that you had said in email was the number one question that people ask you is, Sonny, when will we have warp drive? That is obviously a very important question, and that is something that you have been working on for decades. But folks need to be aware that you are harnessing zero-point energy in the lab right now. This is scientifically validated real-world ZPE. This is not, this is not quack science. You're doing it. You're making it happen.
Yeah, we have chips that generate 3.5 volt capacitive discharges in dark RF shielded enclosures. And then we have chips that now exhibit steady state current and voltage over long periods of time. And so we are working to improve performance such that we have chips, about the size of your pinky nail, 5 millimeter by 5 millimeter, that generate 1.5 volts and 25 microamps. And so, you might think, golly, that's not a lot of power. Well, the beauty of the last 10, 15 years is that the low power electronics market has exploded. And so there are tons and tons and tons of applications for us to go after with a chip like that. So with that kind of power level, we can run a tire pressure monitor system, a glucose monitor, a remote control, a key fob, an Apple AirTag, Internet of Things device, photophoretic displays on grocery stores, NFCs on your credit card, RFID. I could just continue to go on.
One of the other things that's really exciting is because you're using chip fab technologies, right? You can take advantage of all of this progress from the semiconductor industry. And again, you've got these things on a chip. So a single cell, a single junction or a single ZPE harnessing thing may only generate a tiny amount of power. But if you could put these on a chip, then you can scale it.
Right. That's definitely something we're thinking about, Tim. What we call our minimum viable product, right? The 1.5 volts, 25 microamps. That's a single layer chip. So we have a silicon substrate, and then we've got a whole bunch of those little custom Casimir cavities and serial and parallel to get to the voltage and current that we need. But that's just a single layer of devices, and that only takes a certain number of masks to create that level of complexity. And if you look at the number of masks it takes for us to do a single layer of devices versus what you might see typically done in a CPU, they're orders of magnitude different. So one of the easy knobs that we can turn for scaling is to make our chips multi-layer. So metaphors usually help communicate. So let's give a little metaphor for this. So instead of being like a parking lot full of cars at a Walmart where it's a single layer parking lot, what we're talking about is making it like a multi-layer car park at the airport where you might have 6, 7, 8 layers of ability to park cars on top of one another, if you will. And so in that way, that's one of the things that we intend to explore over the next 4 or 5 months is making our devices multi-layer. We've already worked really hard to get the nanofabrication recipe compatible with that vision. And so when we do things like that, and if we also do die stacking on top of that, then we could have, for that same 5 millimeter by 5 millimeter chip, it might be 100 times more power with the same footprint. It'll still be less than a millimeter thick. I mean, we'll put plastic on it, and then it'll probably be a millimeter thick. But then we have chiplets that, or chip assemblies that are 100 to 150 times the original power level, and then we can connect a bunch of those together on some kind of a PCB to get to higher power levels that might have more interesting applications. Like this is this is a 3D print. This isn't a prototype. Make sure I'm clear about that, right? We are making chips. We're doing this for communication purposes, right? So, but put a lot of these chips together onto an aggregate assembly to get to a half a watt, 2 watts, 5 watts, a kilowatt, right? Whatever your particular application might be, with the operative question, what's the dollars per watt, right? How do you, in the process of making these things and optimizing the manufacturing process to attack the cost, scaling it to further attack the cost, improving the performance to further attack the cost, right? So, for example, so I'm going to switch gears from the technical into the dollar side for just a moment to tell a story, like how you have to think with both sides of your brain, right? When you're doing a business, right? So, we're certainly focused on this performance, but we have to communicate the vision. And so, this is let's say 3.5 watts to make it easy. You don't actually need this much to be able to have an immortal iPhone, right? So if you look at an iPhone, it's already has a battery in it. So let's assume we leave the battery in it, right? Because we want an electron bucket. We want something that we can put electrons into. So you leave the battery in. It's not in manufacturing, it's actually not that expensive. It's expensive as hell to replace it, but when they first build them, it's not that expensive. Leave the battery in place, and then you would only need about a half a watt, right? Like a little Casimir generator, power cell, whatever you want to call it. That would be the faithful hamster turning the wheel, putting electrons into the electron bucket, right? And so over a 24-hour period, it would put in enough electrons to fill the battery completely, if you will. And so in that kind of a hybrid mode, right, we could offer up an immortal iPhone, if you will. But the very first ones would probably be a little bit of an expensive upgrade. It might be like $500 upcharge to be able to provide that. And so while it's exciting, you also have to balance how much would somebody be willing to pay for that, right? And so at 500, it's not going to be everybody, but a handful of people might be interested in that. And then we can continue to, scale the economics. So maybe, 5 years we're in iPhones, and then 10 years we've gotten the economics down where we can sell 1 kilowatt bricks, right, for people that own electric vehicles. And the 1 kilowatt bricks provide 24 kilowatt hours of energy, that the electrons, again, going into the bucket, right? And so for 99% of the ways you might drive your electric vehicle, you're not going to have to plug it in. If you do like a 1,200 mile drive, you're going to have to plug it in because you're going to outrun the hammer, right? So
the comparison you made earlier to solar panels is kind of stuck in my head. And, in so many ways, what you're describing seems like the infrastructure and the products and just the entire process involved really does have a lot of parallels, though. So I'm like, okay, I could see how this could be used for numerous applications where you want to trickle charge something, just like solar panels. I think Tesla is selling rooftop panels to charge Tesla vehicles right now and things along those lines. So it would be like that, except that since you're harnessing ZPE, essentially the sun is always shining.
Right, exactly. You can't field from the quantum field, right? It's everywhere. You can't put it in a box and prevent it from getting in there, right? The quantum field is directly part and parcel of atomic structure, like atomic orbitals are all integrated into it, right? So, that does provide a really good characteristic of it compared to some of its counterparts. But the other real thing that you have to think about is the economics, right? And so, in order to start to be really attractive for taking your house off the grid, right? You're probably going to have to get down to maybe no less than $100 a watt, and even then, that's only a very small subset of people would want to spend the money for something like this that would allow them to maybe have a cabin in a remote location or cut the cord for their house, if you will. I think in order to really start to be more broadly accepted, we probably got to be around $50 a watt, right? So plenty of opportunity of room for improvement, right? And so we've thought a lot about all the different steps we'd have to go through in the phases and the different things that we have to do to get there. But the beauty, just to go back to the beginning of the discussion, there's a market now right, at this entry point that I'm talking about, that gives
Yeah.
us a really good opportunity to move the company into the state of being default alive as opposed to default dead, right? When you're a company and you don't have a product and revenue in this venture capital startup domain, right? Your company's default dead, right? And so you want to try and get to product and revenue so that you can be default alive. So, yeah.
Yeah, I'm going to call it default amazing. That's where
Okay.
I'm stuck on this. But so one of the other things, and I'm cribbing some notes here from an amazing interview that you did with Joe Rogan just a while ago, and one of the things that you'd said was the physics that you're involved with at Casimir have applications to warp drives. So there's a crossover. I guess some of the learning that comes out of working with this ZPE generation technology also helps you understand maybe the structure of quantum foam or, things like that apply to the warp drive space as well.
Right. If you look back to Alcubierre's original paper, 94, 95, whenever he published it, and he goes through and explores the mathematical form that something might need to take to utilize the loophole in physics that you can expand and contract space at any speed, right? And we see this when we look at the early cosmos. Right after the Big Bang, there was this inflationary period, and points moved away from one another very, very fast. And so Alcubierre, motivated by his interest in science fiction and Star Trek, is like, what does this model need to look like? And so he does some work and publishes a paper. But part of what he needed to make this idea manifest is exotic matter. In general relativity, the language that's applied there is exotic matter. And so,
Yeah.
I suppose as a quick preamble, if you think about everything that we know of physics today as a Venn diagram, there are two circles on the Venn diagram: general relativity, quantum mechanics, right? The macro world, micro world, cell phones, GPS, right? These two circles touch at a tangent point. They don't overlap. They touch at a tangent point. They're connected through special relativity, the Dirac equation, and quantum mechanics. That's just a preamble for background. So Alcubierre is doing some work in general relativity, right? And he comes across a model, the Alcubierre warp metric, that requires exotic matter, which is effectively negative mass, right? We all understand positive mass, right? We've all had a little brother that hit us in the head with positive mass. We understand positive mass, right? But and we understand zero mass. That's the absence of anything. But then, what is negative mass? What does that even mean, right? That doesn't make any sense in the context of general relativity. General relativity doesn't provide any mechanism to make something like that manifest, other than just the mathematics, right? So Alcubierre rightly highlights in his paper, this is an issue, violates several different energy conditions, might mean that this idea is non-physical. But then he rightly acknowledges the fact that, remember, I said there's two circles on the Venn diagram: general relativity, quantum mechanics. Quantum mechanics has this thing known as negative vacuum energy density, which is what is made manifest in a Casimir cavity. There's a deficiency in vacuum energy here. So this is a negative vacuum energy density that is manifested inside the Casimir cavity. And so Alcubierre highlights, although we don't know in the context of general relativity how to make exotic matter, we do know from quantum mechanics there's this way for us to make negative vacuum energy density, which is mathematically identical, right? So, but maybe the operative question is, right, because these two circles don't overlap, right? How do you take this out of here and put this into here, right? How do you map that, right? And so that's something that needs more thought. But with that said, that's still a very important conjecture on his part. And it says that in the quest to go try and pursue something like that and see if it can be reduced to practice at some point in the future, this is something that one would want to think about. And so we published a paper connected to some work we were funded by DARPA Defense Science Office, working on these custom Casimir cavities that I'm talking about, the plates and the pillars. When we were looking at how the quantum field responds, getting a property here, when we were looking at how the quantum field responds to the presence of the shapes that we're putting together, we wanted to make sure that the pillars along the midplane, that the diameter that we picked for the pillars was not too big, such that they shielded themselves from the very quiescent protected lagoon we're trying to create, right? So we have some really massive code that we wrote to go through and model the vacuum field fluctuations for this arbitrary three-dimensional shape, and convinced ourselves that we knew how to make pillars that would preserve the perturbed state, the negative vacuum energy density, the reduced energy state in the quantum field inside the material that makes up the pillars, right? That's kind of important when you're trying to figure out what happens when you look at can the electrons tunnel back? But during that analysis, when we were looking at the energy density distribution around the pillars, right? So you've got the walls of the cavity, and then you have the basically that big pole that's in the center, if you will, this cylindrical shape that just kind of goes straight up. When you look at how the quantum field responds to that, the distribution of negative vacuum energy density, if you took a section cut through it, you just cut it in half, it ends up with around the central pillar shape, there are two lenticular shapes, kind of look like maybe a bean, if you will.
Okay.
But if you compare that section cut to the plate pillar structure, you take an Alcubierre work metric and you cut the spaceship in half, right? There's like a ring that goes around a football shape that's in the center. If you cut that in half and then you look at the cross section, it almost looks like what we have in the Casimir cavities, these custom Casimir cavities. And so we thought, well, that's really neat. I wonder if we looked at a perturbation of the shape where instead of a cylindrical rod inside a gap between two plates, what if we looked at a sphere in the center of a ring? And so I got my little prop here. If you look at some kind of a ring, right, that has a ball in the center, right? And so the shape of the size of this is like maybe a few microns across with a 1 or 2 micron ball in the center, right? The energy density distribution around something like this actually matches the requirements of the Alcubierre warp metric. And so we published a paper the work we were doing for DARPA was exploring if we could go through and harvest electrons, if you will. DARPA's very interested in the power. They had no interest in the idea of space work. Let me clearly communicate that, right? But this was just an accidental finding. In the process of looking at that, it's like, hey, wait a minute, that looks just like the energy density required for the Alcubierre work metric. And so we published a paper in EPJC that documented all this, where you can make, and you can, they have 3D printers that print down at the level I'm talking about, right? Where you can 3D print something of the sizes I was talking about, and then metalize it through some kind of electroless process. And maybe you would set it up so that you could beam some photons through the center of the ball and put a bunch of those like a train, one right after the other, and just go through and do a test and see if you can change optical property. So if you have an unfettered photon moving relative to a photon moving through the racetrack, compare the optical properties of the two. And so the significance of the paper is that for the first time, we can propose a real structure that physicists could build, and we have the tools to build it, and then go conduct an experiment where the details have to be done to figure out what does the experiment need to look like to be able to detect it. But in terms of what would you build, you can clearly say what you need to build. And so, sorry, go ahead.
Well, we were talking about culture earlier, and this is kind of one of the long-term challenges. And I'm sure this is something you've struggled with as well. But, the moment you mention the Alcubierre drive, people come back with this negative energy requirement, and they're like, it requires tons and tons of energy, and we don't know how to make this, and it's negative energy, and it can't be done. And going to your design Yeah, I mean, again, the toroidal field itself massively lowers those energy requirements. And now what you're doing takes that even further towards being a realistic proposal. So I guess one of the things I was wondering was, do you see this moving towards being something that we can actually build in the real world? And I guess the other part of that is, how do we overcome this psychological or cultural barrier that just says, look, it can't be done because this paper in 94 said so?
Right. Um, yeah, so certainly I think it's interesting to be able to say in our quest to power this little device, the work actually might be relevant to the idea of a space warp, right? Because it's like if you ask a hypothetical question, right, when you crack open the engines on the USS Enterprise, right, what might be in there? Well, I mean, it could be trillions of these things all stacked up together. I'm being theatrical for effect, right? But I think everything that we're doing with this type of stuff is trying to develop a deeper understanding of the quantum field, and maybe even on that physics Venn diagram, we're providing an opportunity to maybe add a third circle, right? That not only connects the two circles, right, but also maybe inscribes just a little bit where nothing's currently mapped there, right? And so, if we're able to uh, open up a new domain where math and physics is predicting stuff that's never existed before, that provides opportunities for new technologies too, right? That's the cool thing of trying to explore the frontiers of what we know, right? So yeah, that's yeah.
Yeah. Well, the reason I had kind of moved on to the warp part was one of the things that you had mentioned to me, again, when we were talking about doing an interview, was this idea of getting to space versus through space. And one of the things that I have seen is the vast majority of financial investment has gone towards getting us to space, right? I mean, again, there are something like 14,900 satellites in orbit, and it's chemical propulsion that put all of them there. That's getting to space. It has value. It has commercial value for communications and GPS and many other things, but it's not through space, which is Mars and beyond that you talked about earlier.
Yeah, right. That's definitely, I do get a chance to do a lot of discussions with students all over the globe about space exploration, and no surprise, I tend to focus on the power and propulsion aspect. And so, one of the messages I try and make sure I communicate in those engagements is there is a big difference when you're optimizing getting to space versus optimizing moving through space, right? And like you said, we live in an age where we are mastering the art of getting to space, right? We've got SpaceX came out of nowhere, and all of a sudden they're dominating the to space market. They have boosters that can land and get reused. They got a really big one they're trying to perfect. You've got Blue Origin that's trying to pioneer some very large spacelift capability. A number of smaller companies, Rocket Labs, Relativity, Firefly, that are all working on launch capabilities, and all these things map to that, to space, that preposition, to space, right? And so, but when you get into space, how you put energy into a spacecraft can change, right? So when you're on the surface of the Earth and you're trying to get to orbit, you have to be able to lift all of your weight to be able to lift off the ground against the pull of gravity. You have to exceed that, right? And so that sets a certain performance threshold that you have to meet. And so chemical propulsion tends to be it is the ideal solution for getting mass from the surface of the Earth to low Earth orbit, right? Where you've got to try and put an enormous amount of energy into a payload in 8 or 9 minutes. And so the power levels for that end up being like gigawatts, right? That's huge. And so chemical propulsion is really ideally suited for that, because all that energy comes from, the specific heat of combustion of the fuel and the oxidizer. Think of those molecules as having springs between them, right? And the combustion process allows some of that energy in the springs to be put into the propellant exhaust, if you will. And so chemical propulsion does a great job of solving that problem. And so optimizing for that looks like, Falcon 9, Atlas 5, Starship, New Glenn, pick your favorite rocket, right? That's an illustration. Those are all illustrations of optimizing for that problem. When you're in space, you might remember having seen video from the astronauts when they're on EVA. They've got little cameras up here on their head, and you can see their hands in the field of view, and they move stuff around. And in some cases, they might be moving something that's really heavy. Maybe they're moving something that's 500 pounds or 1,000 pounds, and they're moving it with finger pressure, right? And so to give people an experience that might help them map to that is when you go to get on a boat, right? You reach out and you grab the rail of a boat, right? You can still actually move the boat a little bit side to side, or at least reasonably sized boat, right? Not a huge one, but that's like 0G in 2 dimensions, right? So even though the force you're applying would never lift it against the gravitational pull of the Earth, right? But you can still move it side to side. When you're in orbit, that then becomes the same thing, but in all 3 cardinal directions, right? So when you're in space, you no longer have to have something that provides a thrust that's equivalent to, its Earth weight, if you will. You can use systems that have much lower thrust values. And so that allows you to use different forms of propulsion. So like sticking in the context of known physics, known engineering, electric propulsion is a very prevalent form of very efficient propulsion that's all over low Earth orbit, geosynchronous, and we actually have a couple of science missions that are making use of that. And so electric propulsion as a capability is a scenario where you use, instead of using combustion, the specific heat of combustion to put energy into the exhaust, you're using electric and magnetic fields to ionize a gas, pull an electron off, and then use the electric and magnetic fields to accelerate the ionized propellant out the back of the thruster. And so the efficiency of that, how much energy do you get out of a kilogram of propellant versus what you get from chemical propulsion? That's way higher. And so let's finish with this. To illustrate the problem of through space versus to space and why the optimization is so important here. It takes about 9 kilometers a second to get a payload from the surface of the Earth to low Earth orbit. If we want to send human beings to Saturn and we want to get them there in 200 days, the amount of energy that's necessary to do that is 2 orders of magnitude higher, right? Sorry, it is an order of magnitude higher than what it takes to get a payload from the surface of the Earth to low Earth orbit. So it's like 150 kilometers a second, right? It's plus or minus 20% there, but it's a huge number compared to the energy that's required to get to orbit. So all that to say, if you were to apply the rocket equation and try and figure out, can I use some chemical propulsion system to solve that problem? Yeah, that's not going to look good, right? It's going to be, if your Excel sheet can handle the number of zeros, you're going to have a huge amount of propellant and just the tiniest little payload, right? So all that to say, chemical propulsion doesn't solve that problem. So this goes back to the moon, Mars, and beyond. That beyond word is really important, right? Because chemical propulsion can't solve those problems for us.
Well, and in addition to that, I have been doing a lot of study lately on nuclear propulsion, and there are many different ways to skin that cat. But one of the things that jumped out at me was it is not as clear cut as a progression from chemical as I at least first believed, and I think as many people first believe. So that takes us back towards warp drives. That takes us back towards your work. I mean, I had always thought, I'd always kind of envisioned this progression of, okay, today's rockets to tomorrow's fusion drives, right? Like from the Expanse. And then from there, we go to the Star Trek future of warp drives. But like heat dissipation is a major issue with fusion drives. And that is just one of many challenges that are involved there. So I think the work that you're doing, that makes it all that more important, right? Maybe we could leapfrog nuclear entirely and go straight to warp.
Right. Certainly that'd be wonderful. Maybe we can finish on the when will we have warp drive question. But before we do that, I want to go back and address a little bit what you just talked about there. In my mind, when I'm communicating with students about this domain, and I try and communicate different ways we can solve the problem. If you want to stick within the context of known physics, known engineering, nuclear electric propulsion, not nuclear thermal. That's that while it is a useful, it's a useful and interesting thing, that it has some issues. So that's a discussion for another day. But nuclear electric propulsion, we've got a nuclear reactor providing electric watts to some form of electric propulsion as a capability. If you're a mission planner, you're trying to figure out what can I do with these Lego bricks. NEP as a capability in any architecture actually allows you to send human beings anywhere in the solar system, right? In terms of interstellar, yeah, it's many thousands of years to try and do something interstellar. So from that standpoint, it does have its limits. But known physics, known engineering, we know how to build nuclear reactors. We've got electric propulsion all over the place, right? All of Starlink has Hall thrusters, so there's thousands of electric propulsion systems on orbit. But it's interesting to think that unlocks those types of possibilities. Fusion propulsion, right? We don't have terrestrial fusion reactors yet. Contrary to Iron Man, we don't have a gigawatt, fusion reactor providing power levels like that. While it's known physics, it's not known engineering. We still got some work to do. But fusion propulsion as a capability allows us to do quick solar system transiting, if you will. And it might start to unlock an interstellar concept if you're willing to wait 100, 150 years, right? It kind of pulls that into the realm of possibility. We just got to figure out the engineering. But then you get to the frontiers of what you're pulling on, right? Space drives, warp drives, wormholes, what's beyond what we know that really could help enable rapid interstellar travel. And so that's like the asymptote, if you will, of the different things we might go try and run down. And certainly that's something that drives me, right, and keeps me interested. And one of the most common questions I get when I do speaking engagements is, "Hey, Sonny, when are we going to have warp drive?" Right? And it's I appreciate the question 1,000%. I get it, and I'd love for it to be in my lifetime. But my crystal ball doesn't work any better than anyone else's, right? I don't know if it's 2 years, 20 years, 200 years, or never. I don't know. But I'm going to say this: I know what I need to be doing next, right? And let me kind of illustrate that a different way. I taught some classes at the International Space University over in France, in Strasbourg. And they have a wonderful cathedral there. The Strasbourg Cathedral is just breathtaking. And but the interesting thing about history of this beautiful cathedral, the spires are 500 feet tall. So it's just hard to think something that old that's that big. They started building that cathedral in like 1100 AD, and they didn't finish it until the mid 1700s. So what that says is the people that built the foundation or the basement, however you want to say it, they had no hope of seeing the finished product. All they could do was just imagine what it might look like. But they knew what they need to be doing next. And so they had to do their part so that they could then hand off the task to the next generation to do their part, build the columns, and the other one to do their part, to build the buttresses, to build the roof, and so forth. And so several hundred years later, this thing is completed. And so I think it's important to remember, in a day and age when you text somebody and you get impatient because they don't text you back like right away, right?
Yeah.
It is important to realize that, one of the strengths of humanity working together is not only just in the here and now, shoulder to shoulder, but over generations, right? And so, again, I don't know when this will happen, but I know the things I need to be doing next. And I know, there's some things that I can do along the way that help me continue to fuel the effort to go try and make progress, right? So, I know what I need to be doing next, right? So
Amazing, amazing. Well, Sonny, that is a wonderful note to close on. Let me thank you so much for your time today. Again, truly an honor to be able to interview you. And actually, as I close, let me close by asking you, what do you need to do next? What's coming up for you in the next few months?
Right. So what we're doing right now is just continuing to try and improve performance of the prototypes that we make, working on different materials and morphologies. So we're going to be making a lot of prototypes very quickly moving forward. We've learned how to make chips in less than 2 weeks, right? We can design it and make it in a 2-week sprint. So that'll allow us to iterate really quickly. So I routinely remind the team we're trying to employ the SpaceX model, right? You got to move fast and try and cover a lot of ground as quickly as you can, right? So.
Amazing, amazing. Thank you again so much for your time today, sir.
Oh, absolutely, Tim. Thanks. This was a joy. Appreciate it.